You know, for over a century, our whole picture of gravity has been built on one single monumental theory. But what if there was another way? A road not taken that starts from a totally different place, challenges some of our most fundamental ideas, and maybe it solves the biggest mysteries in the cosmos without needing to invent things like dark energy. Okay, let's dive into the deep, foundational debates about gravity that are really shaking things up.
So here's our game plan. We're going to start with the reigning king, general relativity, and really look at why, even with all its success, scientists are still searching for something more. Then, we'll get into the really cool stuff, the radical alternatives. We'll compare how they see the universe, check out a mind-blowing recent experiment, and finally, we'll ask, what would a universe running on these different rules actually look like?
All right, first up, the theory we all know, Albert Einstein's absolute masterpiece, general relativity. And honestly, it's impossible to overstate how successful this theory has been. And that's not an exaggeration. For more than a century, GR has been the bedrock of modern cosmology. I mean, from bending starlight and the wobble in Mercury's orbit to the discovery of gravitational waves, it has passed every single test we've ever thrown at it. Just with flying colors, every time.
This central idea is it's so beautiful. Gravity isn't some spooky force pulling you down. No. Instead, the mass of the Earth literally creates a dip, a curve, in the fabric of space-time itself. And what we feel as gravity is just us following the straightest possible line through that curved geometry. Space-time isn't a static stage anymore. It becomes a main actor in the whole cosmic drama.
So, the big question is, if GR is so perfect, why are we even having this conversation? Where are the cracks in this beautiful theory? Well, for all its power, the theory leads us to some really bizarre, really uncomfortable places. It paints a picture of the universe that just feels, well, incomplete. Okay, so right at the heart of every single black hole, GR predicts a point of infinite density, a singularity, where all the known laws of physics just completely break down. They stop making sense. Then, to explain why the universe is expanding faster and faster, we had to basically invent this mysterious stuff called dark energy, a placeholder that supposedly makes up 70% of everything. And maybe the biggest problem of all, GR and our other pillar of modern physics, quantum mechanics, are totally incompatible. They just don't speak the same language. And these huge puzzles are what force scientists to ask, okay, is there another way to look at all this? So let's go down that rabbit hole. Let's explore those other paths. And I want to be clear, these aren't just little tweaks to Einstein's theory. These ideas start from a completely different foundation, asking a whole different set of questions about what gravity and space-time even are. And this is the key. Instead of starting with geometry, with curved space, these gauge theories start with the rules of quantum mechanics. They use this incredibly powerful idea called the gauge principle, which basically demands that the laws of physics have to be the same no matter how you're looking at them locally. This exact principle is what gives us the entire standard model of particle physics. It's unbelievably successful. So the idea is, why not apply that same winning logic to gravity? In this picture, space-time is a flat, static background, and gravity is a force field that operates within it, kind of like a magnetic field. This is a fantastic way to visualize it. Think of general relativity as living in one specific kind of mathematical space, a Riemann space, which only has curvature. But that's just one piece of a much bigger, more general world, a Riemann-Cartan space, which also has this other property called torsion. You can kind of think of torsion as a twisting of space-time, and it's something that's directly connected to the quantum spin of matter. Gauge theories naturally lead you into this bigger playground, which suggests that maybe, just maybe, GR is a simplified version of a much deeper, richer theory. Okay, so let's get into the specifics of how this really builds a fundamentally different picture of reality. We're going to compare general relativity side by side with a specific type of gauge theory called G4V, and the contrast is pretty stark. So right off the bat, here's the first great divide. In GR, space-time is an active player in the game. Its curvature is gravity. But in a theory like G4V, space-time is the fixed, passive arena. It's the stage, and gravity is a field described by potentials that moves across that stage.
Now this is where things get really wild. We are all taught that c, the speed of light, is the ultimate cosmic speed limit. It's a fundamental constant. But G4V says no. What we call the speed of light is actually a direct measurement of the local gravitational potential, meaning it's not constant at all. So near a huge star, it's not that your ruler is shrinking and your clock is slowing down, like GR says. This theory suggests your ruler is just fine, but the actual speed of light right there has changed. And it goes even deeper.
to the very nature of inertia. Why do things resist being pushed? GR's answer is the equivalence principle. Locally, you can't tell the difference between gravity and acceleration. But G for V dusts off a much older, more philosophical idea called Mach's principle. This says that an object's inertia, its resistance to change in its motion, comes from its gravitational connection to every other particle in the entire observable universe. Think about that. Your inertia isn't just some property you have, it's a cosmic conversation.
So you're probably thinking, okay, this is a fascinating debate, but it all sounds pretty theoretical. But here's the exciting part. We can actually test some of these core ideas. Let's look at a recent experiment that gives some serious credibility to this idea that gravitational potentials, the very foundation of gauge theories, are physically real.
The Aharonov-Bohm effect is this famous, totally mind-bending result from quantum mechanics. It shows that a charged particle can feel a magnetic potential even if it never actually flies through the magnetic field itself. Well, this is the gravitational version of that. And it suggests that the underlying potential is actually more fundamental than the force we usually think about.
So in this landmark 2022 experiment, a team did exactly this. They took a cloud of atoms and used lasers to put them into a quantum superposition, sending them along two different paths at the same time. Then, they brought a big mass near just one of those paths. Now, when they brought the atom waves back together, they saw an interference shift. The atom somehow knew the mass was there, even though the difference in the gravitational force between the two paths was basically zero. It was only experiencing the potential.
And that's the whole point. This is huge. This experiment provides real, tangible evidence for a core idea in gauge theories. It tells us that this underlying potential, the thing that theories like G4V are built on, isn't just a mathematical trick. It's a real, measurable part of our universe.
Okay, so if we take these alternative ideas seriously, and we have experimental evidence pointing in their direction, what does that mean for those big cracks in cosmology we talked about? How does this change our picture of the whole universe?
This is really where these alternative models make their strongest pitch. They seem to just neatly solve GR's biggest problems. For example, in G4V, the accelerated expansion of the universe just falls right out of the equations. It's a natural consequence of how gravity works at large scales. You don't need to invent dark energy. Its solutions for black holes are smooth and totally free of those pesky, physics-breaking singularities. And because these theories are built on quantum principles from the very beginning, they offer a clear, logical path towards finally uniting gravity with the rest of physics.
And that leaves us with this one last, truly provocative thought. Maybe gravity isn't a fundamental force at all. Maybe it's an emergent phenomenon, like temperature or pressure. What if the pull between two masses isn't because of a fundamental law, but is just the universe's statistical tendency to move towards a state of maximum disorder or entropy? In that kind of universe, gravity isn't a law you have to obey. It's just the path of least resistance for a cosmos that's always shuffling its own deck. That road not taken, it might not just be a different path. It might lead to a completely different destination, one where we have to redefine what a physical law even is.